So in the previous video, we took a look at this structure and we said this was the simplest carbohydrate. We still didn't give it a name, and we're not going to give it a name in this video either, because I want you to focus on stereochemistry, not the actual carbohydrate itself. And we walked through how to draw the R form, how to draw the S form, how to draw the D form, how to draw the L form. And we said that D and L is just another way to represent R and S. And then we kind of threw in the whole idea of optical activity again. So this was a review topic. We know that these things with chiral carbons rotate light. And they rotate light in a very specific direction. And we can't really determine what direction that's going to be until we put it in a polarimeter. And this is where we get the plus, and this is where we get the minus. Okay, so this, at the end of the previous video, I said, remember, this is called the perspective formula. Okay, so that's what I'm going to kind of call it here. It's a perspective formula. It puts a perspective on things, right? So a perspective formula is basically a structure that has this solid and this dashed wedge on it. That is what we call a perspective formula. Well, we've already been introduced to a new formula here already in this section, and that was called the Fischer projection, or the Fischer formula, right? And we said that in a Fischer formula, these things kind of went straight up and down like this, and we had maybe a carbon up here at the top that had a C double bond O and an H on it, and we had maybe a CH2OH group down here below, and then in the center we typically had a carbon backbone. Well, in this structure, if you look at this structure carefully, there's a total of 1, 2, and 3 carbons in the chain. So 1, 2, 3 carbons in the chain. One of those carbons is an aldehyde group, and here's the aldehyde group there. One of these carbons is involved in a CH2OH group, and here is the CH2OH group here at the bottom. So it's this carbon in the center that represents the crosshairs in the center of the Fischer projection. And that carbon has a OH and an H group on it. So an OH and an H group on it. Okay, so this is a Fischer projection. Notice there's no dashed wedge. Notice there is no solid wedge. It is typically a straight line up and down, a straight line to the left and right. And we mentioned some orientation when we looked at the Fischer projection. We said that we have to understand in a Fischer projection that the groups that point left and right-handed, those are pointing toward me. And the group that's at the top and the bottom, those are pointed away from me. Now, listen at those words carefully. Pointed toward and pointed away. So we are trying to give you insight of stereochemistry here. That is the whole purpose of drawing these Fischer projections, because I don't want to draw a perspective formula every time that I have to draw one of these. I don't want to go through the trouble of writing the solid and the dashed wedge down. Bottom line, that's not what I want to do. I want to shortcut the method if I can. And the way that I shortcut the method is I have to understand that in a Fischer projection, the group at the top and bottom go away, and then all the groups that point left and right, they point toward me. And then when that happens, look at what happens here. Something magical begins to take place. As long as there's no funny business that happens with the structure itself, if the group, the OH group at least, if the OH group is on the right-hand side of the structure, then this is called the R form of that carbohydrate. Or, if I didn't want to use R, the other term to use for right-handed, because the OH group, it's on the right hand, R stood for right turn. Well, the other one that stood for right turn was a D. So this is a representation of the R form as far as the Fischer projection goes, or the D form as far as the Fischer projection goes. Okay, so what if we had to draw the other form, the left-handed form? Well, those are very simple to do. I keep my aldehyde basically up here at the top. Then that's connected to a CH2OH group down here at the bottom. And the only thing that I do is I flip the OH group around. So I put the OH group now over here to the left instead of the right-hand side. Well, if this is the way that I've drawn the structure, and this OH group is on the left-hand side, this is going to be called not the R form, but the S form. That was sinister, that was left-handed. It's not called the D form, that's dextro. The matching counterpart to it is L, so that's levo. So this is the S form of the sugar or the L form of the sugar. So stereochemistry, again, very, very important. Why is it important? Mother Nature, like we said in the previous video, is a very picky person. And she has decided that for your body to obtain a sugar and to metabolize a sugar and to use a sugar, she wants nothing more other than the R or D form of that sugar. So this is the form that we call biologically active. The L form or the S form of the sugars, you can't do anything with. And again, it goes back to the whole concept of putting the key in the keyhole. Sure, it's a key, it's a carbohydrate, but that key is made a little differently than the one that you need to open the door from. So that means that the S and the L forms of these carbohydrates, they don't do anything for you. They can't get processed. There's no biological activity with the L forms or the S forms or the left-handed rotations as far as the 3D shape is concerned. We really do need the right-hand rotation in order to get basically all of the things that we need from a carbohydrate. And if you're not provided the D form, the L form's not going to cut it. There's no activity at all concerning the left-handed form of a carbohydrate, and that's very important. Okay, now with that said, however, please keep in mind that these R and Ds, they can rotate like right-handed and they can rotate left-handed. So you can find an R plus and an R minus or a D plus and a D minus. We're talking about the rotation around the chiral carbon. The rotation around the chiral carbon has to be right-handed. The way it rotates light, however, can be either left or right-handed. Doesn't matter. It all depends on the sugar and what it does when you put it in the polarimeter itself. So that's the take-home message with the Fischer projection. That's the take-home message with the D and the R form. Those are the forms that are important. Those are the forms that are biologically active. Those are the forms that we want to see as far as these carbohydrates go. Now, the problem is that this is a very simple carbohydrate. There's only 3 carbons in the backbone. What if there's 4 carbons in the backbone? What if there's 6 carbons in the backbone? You know, do we still use, well, which OH group? The one at the bottom or the one in the middle? So which OH group do we use to determine if this is the R form or S form, or if we're asked the D form or the L form? So that is what we will tackle in the next video. Again, we kept it simple for a reason, and that's because we wanted you to take away some lecture theory and understand what we're trying to get across. Now comes the point where we can take this sugar of 3 carbons and maybe expand it. Take it to 4 carbons. Take it to 6 carbons. Give me a hexose now instead of a triose, and figure out, is this the left hand or right hand version of the sugar? So in the next video, that's what we will talk about. That's what we'll discuss, and then that will finish up what we're calling the D and L notation as far as the carbohydrates are concerned.